Hello, Professor Penrose. I have to say, as a actual president of the Academy of St. Luke in Rome, all the pleasure and the curiosity that we have to hear your explanations today, but I must say that I will be just very brief because your time is precious and I prefer to hear what you say. But I must add that as a society of artists, we need to keep in touch with the advanced research of human mind. And so that's why we are very grateful to you for giving us your talk today, and that for us is also a right, propitious opening to a sequence of talks that we named in our academy, La Visione, the vision, in the broadest sense of the word. To express our gratitude, the Academy will send you a formal institutional invitation to become a lifetime honorary member of this Academy, in the hope that you will accept to be part of our family. I thank you again. And I leave word to the distinguished art historian, our General Secretary, Professor Claudio Strinati.
Naturalmente per noi, per l'Accademia di San Luca, è un onore immenso e una gioia grandissima poter ascoltare uno dei più grandi scienziati di questo mondo e uno dei più grandi intellettuali di questo mondo. Naturalmente il professor Penrose è un sommo matematico e non può parlare a noi con, come dire, con il linguaggio della sua ricerca, perché non saremmo capaci di comprendere fino in fondo ciò che ci dice, ma in realtà il professor Penrose è un sommo studioso anche di quella dimensione che per noi è fondamentale, che è quella del disegno. Il disegno geometrico è al centro dei suoi studi, dei suoi interessi, delle sue meditazioni. I paradossi del disegno geometrico, una sorta di lingua universale. Ma non dico niente di questo perché adesso la professoressa Antonella Russo, nostra amica carissima, amica dell'Accademia, eminente studiosa, introdurrà il professor Penrose e illustrerà quali sono gli argomenti, le tematiche che il grande studioso svilupperà.
Ecco, thank you, President Maestro Paolo Icaro. Thank you, General Secretary Professor Claudio Strinati. Welcome, Professor Penrose, connecting with us from Oxford. Rose Bowl Emeritus Professor of Mathematics at Oxford University, Professor Penrose has got so many prizes and recognitions that it would take this entire session to list them all, and maybe not even. So, but I just want to mention just a few: the Dirac Medal in 1989, the 1990 Einstein Medal, and of course the 2020 Nobel Prize for Physics, among many others. This is not the first time that Professor Penrose is invited to speak to an Italian audience, but I believe this is the first time that he speaks to an art academy, and in fact, the oldest world art academy. And we really thank him for graciously accepting our invitation. Professor Penrose is invited today to speak to artists, architects, art historians, because he is a true Renaissance man. He's a physicist, cosmologist, science philosopher, and a skilled artist, and a great humanist for his idea on universal consciousness and his ideas on strong and advocacy of human mind potentials are more powerful than any other artificial intelligence resonated within us. So without further ado, I will leave it to Professor Penrose, who will speak to us on force non-periodicity in Plane Tilings, an interplay between mathematics and visual aesthetics.
Well, thank you very much. It's a great honor for me, and I'm certainly very pleased to be elected an honorary member of the Academy. And it's a great honor for me to speak in Italy too, because two of my greatest heroes, Leonardo da Vinci, of course, and Galileo, who is also a good artist, as one sees sometimes from his illustrations. Well, the story I want to talk about begins more or less in, I think, 1952, when I was a second-year graduate student in Cambridge, working in algebraic geometry, actually pure mathematics at the time. And there was a congress of mathematicians. They had this every 4 years, I think. And the Congress of Mathematicians was in Amsterdam this time. And I remember being told by one of my lecturers there that there was this interesting exhibition by the work of M.C. Escher. I've never heard of Escher before, but he said that I would be interested in this work. So I looked at pictures there, and I was particularly impressed. I seem to remember most particularly this picture referred to as relativity. I hope you can see that one with the staircases going in different directions and people walking up the stairs and under the stairs and sideways and all complications. And it's an amazing picture. And I was particularly struck by this one. I came away, and I remember I was on holiday somewhere, and I thought I would try and do something that was impossible, some kind of picture that was impossible myself. And I started to draw various bridges and roads and things like this in an impossible configuration. And then I simplified this and simplified it, and gradually came to, now I have to make sure I can move. Yeah, can you see the next picture?
Yes.
I gradually simplified it until I came across this thing that's now called a tribar. I hadn't realized that other people had, Oscar Reuterswald in particular, had played with a thing like this. It wasn't quite the same, but more or less the same. But anyway, I found this and I showed it to my father, and he showed it to various friends of his, and they found it very difficult to look at because it was paradox. I learned later that it is a wonderful illustration of a mathematical notion called cohomology. The idea of cohomology, if you had all the instructions about how to glue the pieces together, then you work out something which tells you the cohomology element, and this cohomology element, if it is 0, then you can build it. If it is not 0, you have a paradox like this. I don't want to go into that, but I just thought that this illustrates an area of mathematics. It's something I sometimes use for my students to show them the idea of cohomology, where you have something which is locally perfectly all right. There is the ambiguity of how far away from the observer's eye it is. You always have to have some ambiguity in the picture. You can, once you have that, the local ambiguity, you can make that inconsistent, and therefore you can produce this tribar figure. Escher at the time hadn't got one of these things, but when I got home, my father got very excited and started to draw various impossible things himself. I remember an impossible college he drew, and we wrote a paper which we sent. Well, we didn't know, the paper was illustrating various kinds of impossibilities, such as the tribar here, and we didn't know what the subject was. But my father happened to know the editor of the British Journal of Psychology, and he said that he was sure that the editor would accept our paper. So we decided the subject was psychology, and we sent it to the British Journal of Psychology, and it was accepted. Then we gave reference to Escher's exhibition, and we sent a copy. My father sent a copy of our paper to Escher. And he got very interested in this, and he developed it eventually into the next picture, which is his picture Waterfall. And you can see that there are these triangles fitted together in various places. It's not just a simple triangle, you've got sort of basically 3 of them. And the paradox is also in that the water keeps going round and round and round. Before he'd made this picture, he had, you see, my father had developed the tribar into a staircase, which went round and round and round. And this was one of the illustrations in our paper, which we sent to Escher. And Escher produced that into the famous picture Ascending and Descending, which uses this impossible staircase. We were a bit surprised that Escher hadn't used this previously, but in fact he had. In the meantime, before we had done our paper, Escher had produced this picture Belvedere, which you see is a very similar kind of paradox. The way that the top part of the picture is joined up with the bottom picture is inconsistent. And if you had the 2 parts separately and you had instructions as to how to glue them together, you would find that there was a cohomology element which was non-zero. So this represents cohomology. I don't want to talk about that much anymore, but go on to something else of Escher's, namely his tessellations of the plane. Here we see a particular example where the various creatures, a fish and I think a lizard, and can't quite see what they all are. There's a bird, I think. And they're all fitted together in this extremely ingenious way to cover the entire plane. You could imagine you can continue indefinitely to cover the entire plane. There are things called symmetry groups. There are different ways you can cover the plane, and Escher illustrated all these different groups. He had learnt about this from a visit to the Alhambra in Spain, and he realized that ancient artists had made use of these different symmetries. I'm not going to talk about the different symmetries here. I want to talk about something else, but first of all, let me show you that Escher always played around with these things, and you can see in the background there is a tessellation, and then the various birds and the fish creatures come apart, and they do. I thought this is an interesting one because you see, and he liked to make them come together in the middle, and the fish are the nasty creatures, and they seem to, you can see they're grabbing one of the birds. In fact, the fish are under the water and the birds are in the air. It's not, I suppose, relevant here. But yeah, it's one of the, you see that he makes use of these tessellations in interesting ways as you follow it around. And you see, at one time I was in the Netherlands, and I decided, since I had from my father Escher's telephone number, and I was traveling in my car with my wife at that time, and we were driving around, and we were, I believe, in a place near Apeldoorn. And we decided when we were there, because I knew Barn lived quite close to there, he lived in a place called Barn, and I used the telephone number that my father had given him, and he invited me to his house. So I did meet Escher, and it was a very interesting occasion. At one point, he had 2 piles of prints on one side and on the other, and he said he didn't have many left on the ones on his left. The ones on his right, he pushed towards me, and he said, "Would you choose one?" I said, "My goodness, certainly I'll choose one." Here we go. So I chose that one. Escher was very pleased that I chose that one, because he said people don't often appreciate that one. And you can see that there, if you look at the big eye on the right-hand side at the top, and you can see that is the eye of a fish, and the fish scales, as you go back and back and back, the scales get bigger and bigger and bigger, and they become fish as well. And then you follow the fish round anti-clockwise, and you see that the biggest one of these fish, its scales become bigger and bigger and bigger and bigger until one of those scales becomes the original fish. So it's a paradox of logic. You can see the fish are sort of a subset of the scales of this fish, and then one of those becomes a subset. The original fish becomes a subset of it. And so you have a paradox of a set being a subset of another set, which is a subset of itself. And now when I visited Escher, I decided I would give him a set of puzzle pieces. You see, I'd made these out of wood, I gave him quite a lot more than you see here. I can't remember how many I gave him. These are the ones I found in my flat here, and put them together. But I didn't have them put together for Escher. I just showed him this set of pieces, and it didn't take him long to see how they fitted together. And I explained the basis of it. It's based on some parallelograms with certain rules about how they match together. And he then, I think it's the very last painting he actually made based on the scheme which I had told him. I'm going the wrong way. This is his picture called his ghosts. I think it's turned to a right angle just so you can see more of it here. But this is following the pattern of the wooden tiles that I showed him. You can't very well see the connection, but the point is that it's made of a rhombus shape, and the rhombus shape has various rules for how one matches to the next. But the thing about it is, which is different from any of his other pictures, is it's what's called a non-icosahedral tiling. What that means is that if you see, it's all the pieces are the same shape, all the creatures, he called them his little ghosts. They're all the same shape, but some of them are on a different footing from the others. You see, if I take one of these, and you could imagine another one over there somewhere, I may be able to move the whole picture so that this one becomes that one, or it might be another one that could make one of the others, you see, move it to that one. But there are some which I can't do. I might move it to a black one, and if I move it to that one, I have to turn the picture over in some way, and the pattern doesn't match. So they're not all on an equal footing. They're sort of on two different footings, if you like. They're two different classes, and one of them is one way up, and the other is the other way up. Anyway, Escher illustrated other things, and at the same conference, I think he encountered the Canadian mathematician Coxeter, and Coxeter described to Escher how you could represent other kinds of geometry than the geometry of Euclid. You see, the tiling we just seen is basically a tiling of the Euclidean plane. It's what's called a non-icosahedral tiling, but that's the point which is illustrated here. But it's a tiling of the Euclidean plane. But what Coxeter showed him is how you could, sorry, I got the wrong way, make a tiling of a non-Euclidean plane. And you do this by making, well, this is a transformation due to Beltrami. He's a great Italian geometer. And Beltrami had shown how you could represent this hyperbolic plane in terms of inside a circle. And what I like to use as an example, because you can have the whole, including infinity, the whole picture is represented. It's represented what's called conformally. That means that small shapes are correctly represented, but not sizes. In fact, you can see it most clearly in this picture because the eyes of these fish creatures are exact circles, and they remain exact circles no matter how close you get to the edge. It's extraordinarily precisely drawn. I remember seeing the original of this picture, and I was most impressed. I could go right up to the edge, and you could see he kept on going with tremendous precision. It's one of the things about Escher that he seemed to understand the mathematics as well as he did the art. And he really understood that this was a representation of a kind of geometry called hyperbolic geometry. And you can have, if you see the straight lines in this picture, either they go through the center as straight lines, or else they are circular. These fish, you see, they wouldn't know they're getting smaller towards the edge. This is just a representation of the geometry where they are actually all the same size. In this representation, they're all conformally correct. That is, small shapes are correctly illustrated, or if you like, the angles are correctly illustrated. So the angles on the fish's wings or fins or whatever they are, you can see are exactly the same, no matter how close to the edge. So he liked playing with this geometry. He had actually 4 different pictures. I'll show you another one, which is done in color. This is, I think, a circle limit number 3. And you can see when Escher did these colors, he was very, very careful, so that he understood the mathematics to the degree that he was very, very careful to make the colors consistent with the mathematics. The next one is perhaps the most famous one of these circle limits, these angels and devils. And it's again an illustration of hyperbolic geometry. I like to use these pictures because I have a scheme of cosmology in which the actual universe in the remote future or in the past, the Big Bang, you can stretch it out, and the remote future, you can squash it down. And this picture is a very good illustration of how you can squash down infinity till it becomes a finite thing in the picture. And you can imagine that although the angels and devils wouldn't experience it, that you could step outside this picture to a continuation of this world on the outside. And this was an idea that I made a lot of use of later on. Okay, so let me continue and go back more to the tessellations in the Euclidean plane. The next picture is showing you the different kinds of tessellation you can have in the Euclidean plane. You can have the ordinary square tessellation, bottom right, or I should say the usual thing is where you don't have any rotation. You might have these parallelograms, and the parallelograms keep being the same, and the relationship to the pattern is the same. They're congruent with each other, and you have a translational group. The whole thing goes into itself in different directions, but you can only rotate through 180 degrees. For the other rotations, you can have the square pattern where you can rotate through 90 degrees, or the triangular pattern where the triangles can rotate through 60 degrees, or the hexagonal pattern where you go through 120 degrees and the whole pattern goes into itself. So these are very familiar ways of covering the plane. Here, you see a pattern which looks very, very regular. It seems to be made out of pentagons, regular pentagons, which is not possible. You see, the only symmetries you can have are the ones represented here, where you have twofold, threefold, fourfold, or sixfold. And here we seem to have something which looks like fivefold, and that's not allowed. In fact, this pattern, I'll come back to this sort of thing shortly, this pattern has the nature that if you slide it along, it almost repeats itself. You can say, give me a percentage, say 99.9%. Then I could, in principle, find a translation that is a shunting of the entire picture without any rotations to itself, which agrees with itself to 99.9%. And they say, oh, I didn't mean that, 99.99%. I say, oh, okay, then I can find translation which makes the whole pattern go into itself to only the errors where it doesn't agree are 1 in 99.99%, 1 in 0.001% would be what was not where it doesn't match. So it's almost periodic. And this is a whole area which had not really been studied particularly before. I should explain that I was able to find a way of modifying these shapes here, and I'll show you them in a minute, in order to make it forced, so that if you have these little knobs and notches and you want to make them match, then this whole pattern agrees. Now, let me just see if yes, it's the next one here. These 6 shapes, when you fit them together, they will only make that pattern, which I just showed you, non-periodic. These 6 things fit together to make that non-periodic pattern. I remember seeing this mathematician, Simon Cochin, in Oxford, and he said, you see, there was a mathematical project at one point. The question was, if you have tiles made out of squares glued together, they're called polyominoes. I'll show you a nice example later. These polyominoes stuck together, then there was a question of, can you tell whether or not they will tile the plane? You have a finite number of different shapes. Will they tile the plane or not? And the Chinese-American mathematician Hao Wang proved a theorem that if it was true that any set of finite set of shapes which will tile the plane will do it periodically, that is to say in a way which repeats itself exactly, then you could have a computer program which will decide whether or not the tiles will tile the plane. But then his student, I've forgotten his name for the moment, never mind, discovered that this was not true, then there is no computational solution to the tiling problem. And that depends on having a set of tiles made out of, these were made out of squares with modified edges, that was the idea. And that they would fit together. And he, I think, had something like several thousand different shapes. He got it down to about 109, I think, and then the number came down. And then Raphael Robertson, who's a mathematician, got it down to these 6, which you see in the picture here. And Simon Cochin told me that Raphael Robertson likes to get the smallest number down. And I thought, well, I know how to do it with 4 shapes, with 5 shapes, not 6. So I knew I could do better than the 6 that Raphael Robertson had done. And you see that is in the next picture here. This is it is 6. You see, I knew I could do it with 6 because that gives the non-periodic tiling I showed. But you see that the little pentagonal, so little star shape here is the same as the ones that stick out here, but it's the only place where it goes in. So all you have to do is take this piece, glue it onto that piece where you have the little star shape to glue it on, and you glue 2 of them onto this shape, and then you've got rid of this piece and you have only 5 sheets. So I knew you could do it with 5. Let me show, incidentally, the next picture, which shows how the picture is constructed. There's a sort of hierarchical structure to it. You see, you imagine have this big blue and red, I think, pentagon here, and then you subdivide it in this way into 6 smaller ones, the blue ones, and then you subdivide that into 6 smaller ones, the orange ones, and then you have some little gaps, and you've got to have a rule for how you put the smaller tiles into the gaps, and I've satisfied the rule here. And you can go on and on and on. So if you want to see how to construct a picture according to this tiling, you want to say to find some way of assembling these tiles together, the best thing to do is to make a big version of one of them, say a big star or a big pentagon or something like that, and then use the rule I was just showing you, subdivide, 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 and this shows you how to do it. So the way to construct it is sort of in reverse. You don't try fitting them together in the small and seeing how they fit together, because that's pretty difficult. But if you start big and then go down to the small, that's a way of doing it. Anyway, I remember going home and playing around with this for a bit, and I got it down to 5, and I thought that's a bit, I can do better than that. So finally I fiddled around and I managed to get it down to 4. I was quite pleased with that, getting it down to 4. Then I thought, well, I wonder if I can do any better. I fiddled around and I got it down to 2. Let me show you which the 2 are. There are 2 versions of the 2. Sorry, I'm going the wrong way. Here we see the ones I found first are on the left-hand side. They're kites and darts. The one at the top is called a kite. The one underneath is called a dart. And you can only fit them together. I put little notches and knobs and things so that you have to assemble them in the right way. The only way to fit them together is to make a non-repeating pattern like this. I remember feeling a little disappointed when I found this. You think that might be a strange reaction. I think the disappointment was because I thought it's too easy. I mean, if you can have a thing like this, surely this must have been discovered. You probably find it in the Islamic patterns and things like that. No, it doesn't seem to be anywhere. I found that very remarkable that it hadn't been discovered before. I also had this rhombus one. Curiously enough, I was in correspondence with Martin Gardner, who used to have a puzzle page in the Scientific American Journal, and he got very interested in these things. He and John Conway played around with the kites and darts particularly. But in the meantime, I had a letter from somebody. I didn't have it. He sent it to Martin Gardner. And he said to me, is this person talking nonsense or not? When I looked at it, I said, he has rediscovered my rhombus tiling. This was Robert Amann, who became a good big figure in this area, except he died very young, unfortunately. But he produced all sorts of interesting types of non-periodic tiling. You see, these are all non-periodic, they don't repeat. Here we have, it's colored here in a very systematic way. I won't go into the coloring, but you can see that it looks very regular in the way it's done. And it is a kite dart tiling. Let me show you something else. This is again kites and darts. You can see the green lines show that these bird creatures fit together. Unfortunately, I only found these things just too late. Both Escher and my father died a year, or I think something like that, before I managed to produce these tilings, because Escher would have done amazing things with it. It's really a great shame that I didn't find this earlier, or that he didn't live a little longer, because he would have done very wonderful things. But this is my attempt as an Escherization, where you see the green shapes. You see here's a kite over here, and then you see some darts there, and then 2 kites over here. And the darts the kites make a big bird, you see, a chicken or something, and the little ones are the kites. So there you see how you can make a kind of Escherization, which unfortunately Escher was not allowed to do. And we see here a fairly large arrangement with the birds, which I just showed you, made up in a tiling, a sort of Escher kind of picture. It's interesting to show that the hierarchical pattern is illustrated in the following picture. You see here we have the big bird and at the top and the little bird at the bottom. And the way you proceed, if you know, you start with one or the other, and then you replace the big bird by some smaller birds. One big bird, I think, and I'd have to look more carefully. Two big birds, I think, and a little bird or something. And then you replace the little bird by one big bird and one little bird. And then you keep on going. They get smaller and smaller. So each time you imagine blowing them up to the scale of what you had before, and you can keep on going and making a pattern that's as big as you like. I should say that these patterns never actually repeat, as I was saying before, but they almost repeat. For example, this whole arrangement you can see before you, whatever, if you have a legal tiling of these pieces, you will find somewhere else exactly the same as here, but somewhere on the outside of it, it'll change. So it never quite repeats. It keeps almost repeating. So it's almost periodic, but never quite exactly periodic. And here you see the hierarchy. I thought it would be quite nice. I never did this, to make sort of puzzles for people where you have a few extra pieces. Here I have an example of 3 different possible extra pieces. You take one of these and the birds, and depending on which one it is, I would have to look carefully. Some of them are unique. Some of them have, I think the top 2 are unique, aren't they? I can't remember now. Maybe you can read the writing. My eyesight isn't good enough. But some of these are unique, some are not. That is to say, you have the original tiling, of course, is not unique, because even though it's not periodic, and it's 99.99, or however many nines you like, repeats itself, it never exactly repeats itself. And this, some of them, if you have an extra piece like that, then they do, it is unique. And so you never have you have only one way of tiling. I should have said that it's a curious sort of mathematical theorem. You might say, how many different ways to tile the entire plane are there? Well, there are 2 answers, depending on what you mean by that question. One of the answers is that there's only one. And the correct mathematical answer is that there are infinitely many, more than it's a number called LF0, more than the number of integers, 0, 1, 2, 3, 4, 5, 6. It's a bigger number, bigger infinity than that. So how can it be both answers at once? Well, you see, the answer that if you have a pattern, no matter how big you find that one repeated. So if you're only allowed to look at finite subsets, then it's in a certain sense unique, because you'll always find the same pattern, whatever you've done. If it's only a finite region, every finite region is repeated. But if you want the whole pattern, including right out to infinity, then you get a different answer. Anyway, that's a nice sort of piece of mathematics you can play with. Let me show you another. You see, here was one. I think the top one is unique or something. I can't remember now. It does say, if you look carefully at it, if your eyesight is better than mine, you can see what I said. So there are different ways where you have these extra pieces, and it would be quite intriguing to make a puzzle like this with your whole collection of birds like that, and then you add one of these pieces and see how to do it. So I thought that was an interesting sort of game one might have. Now, what I want to show you next is a picture due to the scientist and, well, artist too, I guess, Johannes Kepler, who, of course, was the person who first clearly observed that the motions of the planets around the sun, if you took the Copernican view, that the sun was the center, and you took the planets as they go around, then they form ellipse shapes with one of the focuses being the sun. But this is another interest of Kepler's, and what he was doing, I really don't know. You see, there are lots and lots of patterns which are they're non-periodic, but and he's using different polygon shapes, hexagon, octagons and dodecagons and things like that. In pentagons, you see the picture up here on the close to the top and towards the right. That one I'm going to have something more to say about in a minute. But that's the biggest one. But all the others, he has various patterns which continue for a while, and you can see they're not necessarily periodic. What was Kepler trying to do? My guess, this is just a guess, is that he'd seen that you could have crystals and things like that, which look as though they're periodic. But maybe living things, they have certain symmetries, and the symmetries are not the same as you get for crystals. You have all sorts of other symmetries, fivefold most likely. And I was wondering whether he was thinking that maybe plants were based on things like this. A very intriguing idea. But what's a little bit more intriguing in a way is the fact that I had seen this picture before I got on my route of trying to find non-periodic tilings. I'd seen this picture, but I wasn't thinking about it. It was in the back of my mind, I suppose. And I think this top one here, the one with the pentagons, had made me realize that you can do interesting things with pentagons. Pentagons are not a dead loss. And I think that image came through to me just sort of unconsciously, so that I realized it was not a dead loss to work with pentagons. Now, it's more than that. Here I have this actual picture, Escher's picture AA, I think it was called, and that is it exactly reproduced here. And what I found later, I was giving a talk and pointing this thing out, and I thought, I wonder whether if you filled in these decagons and these sort of double decagons, which seem to be part of the pattern, and what was he trying to do? How do you continue this pattern, for example? People have various ideas. I think these various ideas are wrong because they make it periodic. I have a suspicion that what Kepler in the back of his mind, maybe unconsciously, I'm not sure, had something like the tilings which I came up with later. And why I say that is because of this. I hope you can see in the sort of purple, slightly rotated anti-clockwise, is Kepler's picture AA. And what I found later is that if you put it on top of my pattern in exactly the right place, you find it matches exactly. This was absolutely stunning to me. So you see all the dodecagons, or say all the decagons are filled up in a way which is quite consistent with the decagon subsets here. And even I think there's a little extra line he puts in somewhere that also fits onto this pattern. I have no idea whether he was trying to do anything in the nature of what I finally did, but there you have it. He certainly had something very close to it. Very good piece of insight. Because I can't remember the date of this thing, 16 something or other. Anyway, let me move on to something else, which was also intriguing. Somewhat later, Shechtman found evidence for things in nature, not as big as this one. These things were little microscopic things, but these are actually what are called quasi-crystals. This is actually a regular dodecahedron, and this is not being a periodic thing. You can't make a crystal, which is a dodecahedron. However, you can make a quasi-crystal. It's not called a crystal. At least I'm not sure whether it is now. People keep changing the names of things, but it was certainly at the time called a quasi-crystal because the packing of the atoms and things, I have no idea in detail what they are, but they must be very close to the sort of patterns that I was showing you. Okay, let me move on. This was something which I came about later as a sort of illustration of how difficult it can be to decide whether a set of tiles will tile the plane or not. As I mentioned before, well, these are what are called polyominoes. They're made out of equal squares in the plane, glued together along their edges, and you make some shape, some plane shape. And you can have a finite number of these, and the question arises, can you tile the plane with them? Could you program a computer to say yes or no that the tilings will tile the plane? And the answer is no. There is no computer program. This is what's called a non-computable problem. There is no computer program which will tell you for a general set of polyominoes whether or not they will tile the plane. And this depends upon having some sets which will only tile the plane non-periodically. That is to say, there is no repetition in the pattern. And this is one I came up with, which is somewhat based on one of the ingenious ideas of Robert Amann. And this is the actual tiling that you can get started. And it's a bit hard to see what's going on. It looks incomprehensible. I know I sent a picture of this to Robin Graham, who is an expert at these things. And he said, I have no idea how you do this. How do you do it? So I showed him how it was done. It's based on, as I said, one of Robert Amann's constructions. And it never repeats itself, but you can keep on going. And there is an algorithm for doing this particular one. The thing that's not an algorithm is the general algorithm for all sets of possible polyominoes. But for a given set, you might or might not have an algorithm. There is an algorithm in this case. The simplest algorithm is to look up my collected works, and somewhere you will find in them the way of doing it. Let me move on to something else. Here we have a nice, easy dodecagons. These are 12-sided figures. Hexagons, regular dodecagons, and squares. And it's a nice regular tiling of the plane that you go on forever. You don't need a computer to tell you that this will tile the plane. You just repeat and repeat. But I'm going to do something to this which is a little bit different from that. I'm going to put designs on each of these tiles. These designs are shown here. The dodecagon has these shapes, and the lines, you have to match the lines. So when you put them together, you see, you mustn't just put them any old way. You put them together so that the arcs match each other, and they match each other. You go together, and you can show this will tile the plane, but there is never any repetition in it. I was at a conference and I showed this example, and one of the people there said, well, I'll put this, since I know the rule, which it is designed, it's a hierarchical rule, like the things I've been showing you before. Somehow you build bigger versions of themselves and that sort of thing. And he put this on a computer. So this is, knowing the rules, the computer didn't discover this, I should say, but he put this on a computer, and this is what you see. I thought it's rather an amazing pattern. You can see things sort of almost repeating. Here you have a sort of the arcs fit together. I should say that the little tiles are tiny. See, the little tiny rings there are pretty well the size of the actual tiles. So this is a huge, huge collection of tiles together. And you see these big arcs fit together to form almost a ring like this. And you have little ones which form smaller rings. And you have another one over here which forms a ring. And you might look at the next one and it may be the same, or it may be sort of rotated around, or it may be reflected. But what's around that one is different from what's around this one. So you have local repetitions, but as a whole, the picture never repeats itself. I think it would be a very nice challenge for a computer, somebody to put this on a computer, let it just try and match smaller and bigger patterns without knowing the rule. How far would it get? I would find it remarkable that if it would get as far as this, what I'm showing you here. Anyway, this is a whole area of non-periodic patterns, which is now a big subject, and people all over the world have theorems and go much beyond the things I've been doing. But it's quite interesting to see that they also relate to nature in interesting ways. Now I want to show you something completely different. It's also a picture that I drew myself, but it illustrates a subject. I'm not going to talk about it, but it's something I spent a lot of my life working on, a thing called twistor theory. And it's a way of representing the geometry of space-time in an unusual way. And think you regard light rays, the entire light rays, as more important in a sense than the points. You can define the points in terms of families of light rays which meet each other, and those families give you the points. But what was interesting to me was that when you slightly extend the geometry to make it into a complex geometry, see, when I say complex, that means you're using the square root of -1. These numbers, what are called real numbers, the sort of numbers you measure on a ruler, or infinite decimals if you like. But if you allow yourself to take the square root of -1 and introduce a thing called I, and then there's -I, which also is the square root of -1, and then you make the diagram in the plane where the vertical axis is the multiples of I and the horizontal axis is the real numbers, and you can combine them together to form what are called complex numbers. And I was always very amazed by the complex numbers. I thought they formed a magnificent mathematical structure, but I thought, wouldn't it be wonderful if the world was based on them? And then I learned about quantum mechanics, and I found quantum mechanics is based on complex numbers. So I really got taken in by this. I mean, found it was a very beautiful subject in many ways. The nature of spin in particular was something very beautiful. So I found the twistors, I thought, was a way of combining quantum mechanics with space-time structure, which it does in a way, but it led to a big topic, and I'm certainly not going to talk about that. I want to talk just for a bit. Because I drew this picture myself. It's an interesting configuration known to Clifford. Clifford was a 19th century geometer who didn't live very long, but he did amazing things in his lifetime. And he showed if you take a sphere, now this is a sphere in 4 dimensions, not the ordinary spheres we know. And so it's a 3-dimensional surface in 4 dimensions that he found you could draw circles around them which interlocked each other in a very complicated way. And if you project this down in what's called stereographic projection, down into the Euclidean 3 space, you can see these circles twist around in this interesting way. This is Clifford parallels, and it illustrates that very nicely. And they are fundamental to twistor theory, and the fact that they twist around in a way is really the origin of the name twister as well. I just wanted to show you, just as an example, I like to play around with pictures. In my books, I like to draw my own pictures, and these are examples where you have, these are light cones, space-time pictures. So you imagine a point here, the velocity of light going out on the long lines here, and you cut it in various ways. I'm not going to talk about these things, just to show you what some of these pictures look like. There's another one, a little bit more complicated, which I found was, it explained various features of these light cones and how you chop them with planes and things like that. And then there's another one showing you how you can project these surfaces down into 3 dimensions in 2 different ways. I really just want to show you it's the kind of thing I like to draw for my own books, and I don't trust anybody else to draw. I used to get other people to draw them, and then it was much more difficult because they'd make mistakes, and I'd say, look, that's wrong, you have to correct that. Comes back and, oh no, that's wrong, you have to correct that. So I decided to do the pictures myself. Here's another one which illustrates the second law of thermodynamics in a certain way. And here we hear what the sun is doing. And the sun, you see, the usual view, people think that the sun gives energy to the earth. That's just not true, because in the daytime, you get these photons from the sun, and I have them very high frequency and very high energy from the photon. And the plants use these things to make the low frequency, low energy ones, which go back into the night sky. We only can live off the sun's energy because of the dark sky. If the sun was if the heat of the sun was all over the sky, we wouldn't be able to use it at all. It's because of this contrast between the hot sun and the dark sky. Okay, that's a little bit more of a speech than I intended to make about that picture. Let me end by showing you something else. This is our new, when I call it new, it's been there for several years. This is the Mathematical Institute where I work, although I'm retired and I have an office here. And I want to show you not the building, which is a pretty remarkable building, which was designed in conjunction with some architects by a former part student of mine, certainly colleague, Nicholas Woodhouse. And this was really, he was in control of the whole design, and he wanted to have a pattern you can just about see in the front of the building is this pattern. And I now want to show you a bit more about the pattern. It is made out of, well, you can't too well see here, perhaps, but you can see in the next one, which I'll show you a little bit more clearly. It's made out of rhombus tiles, and I designed this particular way of putting arcs on them. So each of the tiles is the same. I mean, there are 2 kinds of tiles. There's a fat rhombus and a thin rhombus. Each fat rhombus is the same with the same markings on it. Each thin rhombus is the same with the same markings. And when you fit it together, the only way to fit together is in this non-repeating pattern. Maybe you can see it a little bit more clearly here. You have certain rings which close. You have also these decagonal rings which close also. Sometimes they close, sometimes they wander off to infinity. and it's an interesting mathematical issue about what they do. But it's interesting. I remember the tilers had completed the tiling and they went out, and I thought, I wonder, I'm going to make sure they've got it completely right. You can't make a mistake in the middle without noticing it very soon, but round the edge, it's not so clear. So I went round the edge all the way very carefully, look at all the tilings round the edge, and I found 8 mistakes. I put a little piece of paper on each one and showed them how it should be done. I came back a few days later and they corrected every single one of them. I was most impressed with that. So I think it's a nice thing to see if you're in Oxford, and if you have a chance to visit the Mathematical Institute there, that's on Woodstock Road, you will see in front of the building this tiling, which I think is the nicest example of use of this tiling. Lots of people have used them in buildings, but this one I like the best. Thank you very much.
Oh.
Thank you, Professor Penrose. Thank you for this very generous presentation, very dense presentation. And I saw many of us taking notes, and you made happy, especially our young professor, a physicist professor from Max Planck Institute, who I know would like to speak with you and have questions for you. I have just a few notes for art historians. It is very interesting to me that repetition, once again, we are reinforced in the idea that repetition doesn't make style. And also that a lot happens in the interstices of patterns. Also, it is interesting to me that Escher spoke about a sense of emptiness in his work, and that he wished to highlight the ambiguities of vision, of course, where positive and negatives are confused. And it's interesting that also angels and devils are confused. They are interchangeable. And the result of all this is a kind of vertigo that causes the sense of void into the emptiness. And this is a contradiction that it's interesting for us to investigate.
Yes.
I know that Professor and architect Paolo Portoghesi would like to show you his drawing, his homage to you.
Naturalmente purtroppo non
Right.
avevamo il professor Penrose che potesse controllare se
Margini.
era tutto perfetto come lui avrebbe desiderato. La nostra intenzione era proprio quella di magnificare questa meravigliosa connessione della regolarità con la irregolarità, perché effettivamente c'è una convivenza in queste tassellazioni di una legge molto precisa e però anche di una ricchezza di contraddizioni. E in questo senso ovviamente c'è una storia lunga, perché diciamo nel mondo islamico ci sono delle ricerche analoghe, e io ho trovato anche in Borromini questa ricerca dell'ambiguità della geometria che in qualche modo si riconnette alle grandi scoperte fatte da Penrose. Quindi come architetto non posso che ringraziarlo per anche, diciamo, la modestia con cui ha presentato le sue scoperte, le sue idee, sempre mettendole in relazione con qualcosa che già c'era. Ecco, in fondo spesso gli scienziati hanno la mania di inventare, cioè di far nascere le cose dal nulla. Finalmente uno scienziato che viceversa fa nascere le sue idee originalissime da qualcosa che gli è stato suggerito.
Our physicians would like to ask questions. Yes, raise your hand. Don't be shy. This is your time. This is your opportunity. Go ahead.
Hello, thank you. So
Hello.
it's a pleasure to be here. And so I've been examining the notebooks of John Wheeler during the 60s, and the audience may have heard Wheeler's name with reference to black holes and catchphrases such as "it from it." And well, I could have a few curiosities to tell you about some reactions, nice ones, of course, that a conversation or a seminars of yours triggered in Wheeler back then. However, today I would like to ask you something else, hopefully interesting also for our audience. So many geometric pictures in your books, for instance, when representing a sphere or a generic manifold, or what you showed in your last slides a moment ago, have a quite peculiar feature, even if it is not so flamboyant. I mean, that kind of shading with dots that, besides giving some depth, gives some sort of artisanal flavor to these illustrations, as if you could really take them in your hands, so to speak, and shape them. Perhaps it is just an impression of mine, but I think that on some level, they convey a sort of haptic feeling. I don't want to invoke even Berenson's tactile values, but they are certainly different from the typical clear-cut and quite anonymous diagrams of a geometry textbooks. And I think they are elegant and effective in making one feel the heuristic flow of ideas. Since I was a boy, I associated these pictures with your books, so I was quite surprised when I found them also in Wheeler's contribution to the 67 Bateo Encontro. I was just wondering whether there was a nice story behind these and what were your specific motivations, if any, for making those pictures precisely like that. Thanks.
Well, I think I sort of half mentioned before, because I used not to do that. Some of the drawings I would sketch and then a professional artist would draw them. But I tended to find that there were so many times they'd missed the point. Or, you know, should this line be in front of that one or not? And it's very crucial, that sort of thing. And I could get it sorted out eventually by going backwards and forwards. I thought, well, look, why didn't I just draw them myself? So it was more, I think, the difficulty in explaining exactly what I wanted to some other artists, which made me do it myself. And the dots were just this way I found it most easy to express shading. I mean, lines, I occasionally use line shadings, but I just found the dots did more what I wanted, because the lines you have to, I think it's more difficult with lines. I think probably I was taking the easy route by using dots, because the lines will give you some different feeling about the shapes, which may not be intended. Whereas if you use the dots, it really brings just the shapes out and not something else, which is not intended in the pictures.
Thank you very much.
Thank you very much, Professor Penrose. I really appreciated very much this talk. Very evocative, honestly. So I can sort of prepare some question, perhaps, but yeah, perhaps I'm just gonna try to more vehicle another thought that I had from your talk. So it might not be that clear, but I'm just trying to phrase it. I was really yes, I appreciated very much this idea of this non-periodic, in the sense that I really liked how you say that in a sense any finite region can be found to be overlapped, but then at some point then all the rest of the space will never be fully overlapped. So this, of course, yeah, I mean, of course, makes us think of the idea of non-periodicity, and also as an experimental physicist, in a sense of the fact that you can always reproduce something in an experiment, so you can always kind of control the conditions of your experiment to an arbitrary degree of precision, also to a large extension, but you can never kind of reproduce the whole universe in itself. That's gonna be always unique every time, no? So I don't know, there is just this idea between repeatability also of the experiment, like periodicity of a certain portion of space, and a fundamental irrepeatability of the whole universe in itself. So in a sense, the idea really of the history, that there is a history, there is a sort of, yeah, something that cannot really be fully reproduced, you know. And of course, it makes me think of this the non-periodicity of dynamical systems and so on and so forth. And so I was wondering in general whether because we always speak about very small difference between, say, the discrete nature of the perfect symmetries, no? Where there is absolute precision, like 4-fold, 6-fold, and so on, and there is absolute precision, so it's really ideal. But then in these non-periodic crystals or this non-periodic tiling, there is always you cannot get ever absolute high precision, and there is this element of continuity, of continuous space rather than discrete. So I was wondering whether somehow the fact that you can never specify with full precision, like you do, for example, with perfect symmetries, in a sense makes you think, okay, the space is actually continuous. So I have to allow for continuity in order to be able to allow non-periodicity, the concept of non-periodicity. I don't know if that makes sense, but in a sense, the structural space, the fundamental structural space, whether discrete or continuous, it made me think about these things. I don't know if there is not clear, like a clear question, but yeah, just if you have some comments about this.
Well, in my younger days, as an attempting to be a physicist, I was very interested in the discrete and discrete models, and I had this notion of spin networks, which is an entirely combinatorial way of talking about spins. I guess I've moved more to the continuous just because I always used to have this kind of imbalance or battle within myself, in a sense, the beauty of discrete structures and the beauty of complex numbers. And as my research developed, it was the beauty of complex numbers which sort of won out, but I never quite. Let me say something else which your discussion reminds me of, and that is on the other side of the scale. If you're looking at very big things, we're thinking about cosmology, and there you never do get quite repetition. And it's a bit like, I mean, the issue of you get almost repetitions, but things which are not quite the same. And I found that intriguing. And the fact that you can't see in particle physics or something like that, you expect to find the same thing each time. But of course, yes, if you had to wait for many, many millennia or something, you might get different answers because there could be evolution which is not seen at the level we're restricted by at the moment. But these are very intriguing questions. And I would say, particularly in cosmology, where I have my own ideas, which I didn't want to go into here, but yeah, that's true.
Thank you very much. Thank you.
To me, this talk was quite important because we understood that vision has to do with something really much more complex and much more surprising and mysterious than just the process of some photons entering, going out, or in, or exchanging glances and going around and making possible vision. It requires a sort of consciousness. It requires to have a position, a point of view, and a choice to be in the world and to look at a certain, the world from a certain angle. And it requires a choice of a way to be in the world, and a way, and this way of being in the world defines our being humans, to me. This is just to quote a few philosophers, among which Maurice Merleau-Ponty. So I just would like once again to thank Professor Penrose for being with us and for making this first colloquium at the Academy of St. Luke in Rome, a momentous event in the recent history of the Academia. And I really hope that you enjoyed it as much as we did, and we found it extremely fruitful.
Well, thank you very much. No, it's good fun. It's like having the opportunity to show things like this, yes.
Thank you, thank you.
I would like to conclude this very, very emotionally interesting. My mind is boiling, trying to keep up with all the patterns that Penrose and the two youngsters have agitated in my neurons. But I would like to rephrase the invitation we will fly Professor Penrose. Anytime he will like to come, will be our guest in the Academy. So please keep this in your calendar. So consider this as a real beloved appointment. And thank you again.
Well, thank you very much too. No, I bear in mind what you're saying. I hope to be able to take advantage of it.
Okay, we will be waiting for you. Thank you again. Thank you again.